Okay, so in this video, we're going to remind ourselves how to solve polynomial equations. There are two main methods we're going to use when we're doing it by hand, at least. One is using the null factor law, which requires you to factor or factorize the polynomial first, and then use the whole a times b times c equals 0, therefore a is 0, b is 0, or c is 0 knowledge to then solve. You can also isolate x, but that is only possible if you have a single x term that has a power of 2 or 3 or something, and then have a single value at the end. Okay, so if you had x squared minus 3, you could do that isolating x. X to the power of 4 minus 3 would work, and so forth. You've got to have a single x component, not multiple x components spread out. So let's have a go at a few examples, and hopefully that'll bring a few bells. So this first one, we're going to solve 3 bracket x plus 4 cubed minus 24 equals 0. Now, in this case here, we have a single x term cubed. Doesn't really look like it, I guess. It's x plus 4, but in our minds, we can consider that whole thing as a single term, which means I'm going to use the isolating x method. It'd be a lot harder for me to try to factorize this than to isolate x. So I'm going to add 24 across first, then divide by 3, and I'm left with 8 there. Now to undo a cube, remember it's cube root. So cube root of 8 is 2, not plus or minus 2. The plus and minus options only come out when you have the even powers. And then we subtract by 4 and we get -2. Fairly straightforward, I think. Let's have a go at this other one over here. So same thing, we have a single bracket to the power of 5, and all the others are just numbers. So we can use our isolating x method here. So we're going to first of all subtract that 3. The power of 5 like that. So we get 4 divided by -4. And we have that. Now, this would be a problem if we had a positive, if we had an even power. The problem with an even power is you would always need a positive number there, and you would not be able to solve this. We can't take a square root or fourth root of a negative. But because we have an odd power, we can indeed simplify that. So the fifth root of -1 is -1. Because a fifth root, remember, means what number times itself 5 times gives you the -1. Well, if I have -1 in each of the first two, that gives you +1, -1, +1, -1. So you can actually have negative values under a root sign for odd powers. So you get 2x minus 5 there, and then we solve. So we add 5 across, divide by 2, and we get our result. Hopefully that's fairly straightforward. This next one here, we have 3 separate x terms, so we cannot isolate x. So we must factorize it. And remember, the first rule of factorizing is that we always must look for a common factor. In this case, I can clearly see a common factor of x squared. And you'll end up with x squared minus 12x plus 20 equals 0. I have a quadratic factor of x squared at the front. Do not divide by the x squared, otherwise you'll lose solutions. And then I want to see if I can factorize this quadratic. If I cannot factorize the quadratic, I would use the quadratic formula on that. But in this case, I can, because factors of 20 that add to -12 are x minus 2, x minus 10, and that all equals 0. And at this point, we can say that x must be, we can see it must be 2 from that bracket, must be 10 from that bracket, and the one that is often forgotten is 0. Because remember, null factor law tells me that if things are multiplied, each one individually could be equal to 0. So when x is 0, that whole thing is 0. When x is 2, the whole thing is 0. Or when x is 10, that whole thing is 0. So they're solutions. So those three don't require much work because isolating x is pretty quick. And if you have a nice highest common factor like that, it drops out pretty nicely. This last one, though, doesn't have a common factor. Can't be used for isolating x. We need to factorize a cubic equation. Now, I can do that in a couple of different ways. Both ways require the use of the factor theorem. Go check out the factor theorem video for that. But one way requires polynomial long division, and the other one requires equating coefficients. Given that I've mostly taught you long division, I'm going to go with that method, but either is perfectly valid. So our first step, remember, is to find a factor of this, and we use the factor theorem for that. So let's try the value of 1. So we always want to look at factors of 12 first off, and then go from there. So factors of 12, the easiest factor is 1, so let's try that. So we get 1 cubed minus 2 lots of 1 squared, take 11 times 1 plus 12. What does that give you? It's 1 plus 12 is 13, minus 2 minus 11 is minus 13, and gives you 0. Now I put x equals 1 in there, and it gave me a result of 0, meaning the remainder is 0. So therefore, my factor is x minus 1. At this point, I'm going to now use long division, divide it through. Like that. So x cubed divided by x is x squared. And we multiply out x squared times x is x cubed minus x squared, and we subtract. So that disappears. -2 minus a -1 makes it +1. So -2 plus 1 is negative x squared, and we bring the rest down. Then we proceed further. So the highest remaining power is negative x squared divided by the x makes it minus x. And we multiply down. So negative x times x is negative x squared. Negative x times by 1 is plus 2x. We continue on. Oh, plus 2x to plus 1x, sorry. Negative x squared minus a negative x squared disappears. Negative 11 minus 1x is negative 12x plus 12. Last step, negative 12x divided by x gives you negative 12. Negative 12 times x is negative 12x. Negative 12 times negative 1 is plus 12, and we subtract that result. Great, we have a remainder of 0. So all that means is I can now rewrite this thing as, instead, x minus 1, x squared minus x minus 12 equals 0. I'm going to look if I can factorize this quadratic. In fact, I can. Factors of negative 12 that add to negative 1 are negative 4 and positive 3. So therefore, I find that x equals negative 3 from this bracket, 1 from that bracket, and 4 from that bracket. And that is a brief reminder of how to solve polynomial equations.